Hi, my name's Tom Dick. I'm a math professor and a math advisor for Texas Instruments, and this video is part of the TI-Focus AP Calculus series. We're going to be looking at using the TI-84 to illustrate the analysis of functions based on graphical information. We're going to use as an example a question we made up similar to those in the 2020 AP BC exam. The question we're looking at, we're presented with a graph that's shown here over the interval from -1 to 10, and this graph is presented as the derivative of a function. Now, the analytic form or algebraic form of this function was not given in the problem, but I have produced a function that fit the curve pretty well. And that's in order to illustrate some features. So we won't really be using this algebraic formulation, but I needed it in order to produce this graph. So the first thing we're going to take a look at is just using the graph, what can you say about the derivative of the function? So let's activate the derivative graph. We'll go to the y equals menu, and you can see it, our y2 is already set up as the derivative of y1. So we'll turn that on for graphing, and let's take a look. And now we see the derivative of the function whose graph is blue is this graph that's in red. In the stem of the problem, it was given that there was a horizontal tangent to the blue graph at x equals 4.2. And that's where we see this maximum. Sure enough, if we take a look at the red graph, it changes sign from positive to negative right at 4.2. Okay, now let's go back to the y equals menu. This time I'm going to turn off the derivative, and now we're going to turn the tables a bit and actually think of the blue graph as the derivative of some other function. We're given that this function who has the blue graph as a derivative has a value of -7 at x equals 0. So notice I've entered -7, and now to create an antiderivative, I'm producing an integral function with a lower limit of 0, upper limit of variable x, and the integrand is the function whose graph is blue. And so this is producing an antiderivative with a value of -7 at x equals 0. So we take a look, there was our original graph, and now this will take some time because it's actually calculating a definite integral for each x value. And we can see that quite a bit of the graph is off the screen. So I'm going to change our ymin and ymax. Let's go ahead and triple the values on ymin and ymax so we make sure we get the entire graph on screen. So I'm going to make my ymin, instead of -3, let's make it -9. And our ymax, instead of 4, let's make that 12. And now let's regraph and see if we get a better look. Okay, you can see that kind of squashes down the look of the graph of the blue graph, but now we've got a better fit of a window for our antiderivative graph. Notice that it is equal to y value of -7 at x equals 0, and we can see that where our blue graph changes from increasing to decreasing is the location of an inflection point in this graph. Also, where our blue graph changes sign from positive to negative, our antiderivative graph should have a maximum there. So I'm pointing out where that inflection point is approximately at 4.2, and at x equals 9, where there was a 0, and the derivative, the blue graph changed from positive to negative, we have that maximum. So this is fitting all the qualities that we want. Now, in this particular problem, we were also given a different value for the antiderivative. We were told that it was equal to 12 at x equals 9. So I'm going to put in 12 plus a definite integral function that starts with a lower limit of 9 and then an upper limit of x. This should be another antiderivative, except it's fitting a different initial condition. So as we produce this, it'll be interesting. Will this really look the same as the antiderivative? It's supposed to be the same function because these were two function values for the same antiderivative. And sure enough, you can see that this magenta graph is hugging the graph, even though we used a different initial condition. This initial condition told us that the y value is 12 at x equal 9. But we can see all the information is the same, and we get another way of expressing the antiderivative. Now, in this particular problem, there was another function that was posed for which an improper integral needed to be analyzed. So we want to take a look at this because I think this was kind of an interesting function. This function was equal to the function in blue, our y1 here, and it was the denominator, and the numerator was its derivative. So I'm creating a function that has the derivative of y1, which is our y2, divided by the original function y1. This new function up is y3, and again it's going to be the derivative of our original function y1 divided by y1. So let's take a look at the graph, and it's this black graph, and we can see where our original function is both increasing with a positive derivative and positive y values. The quotient is positive. Where we hit that max and the blue graph starts to decrease, but we're still positive. Now we have negative values on the black graph, and then where our blue graph crosses the x-axis, we have a vertical asymptote. And that was the subject of the improper integral question. Well, that winds up this short video. For more resources like these, please see education.ti.com.